Okay, so it is time to begin. Welcome to the last session of the conference. Our first speaker is Kalai from Hebrew University. Okay, Professor Kalai, we can begin.
Hi. So I hope you can hear me and you can see me. So I have this opportunity to use a Blackboard lecture, and I hope it will work well. So first of all, I want to thank the organizers for inviting me, and I want to thank Tawfiq Mansour for his great work in running this new journal and in this series of conferences, and also in the beautiful interviews he's conducting, which I think is a great contribution to the Combinatorics community, to the Israel mathematical community, and to the entire mathematical community. And I will talk today about the G conjecture and beyond the G conjecture, algebraic combinatorics of cellular objects. And let me see if this will work. You should. Okay. So, okay. So beyond the G conjecture, so I will start the lecture by telling you about the G conjecture, which I think we now can call the G theorem. Well, it was a theorem earlier for polytopes, but now for simplicial spheres. And then I'll talk about some direction beyond the point we reached. So I'll talk about finer invariants of simplicial sphere. I'll talk about flag numbers of general polytopes and the so-called toric G numbers. I'll mention the 3 to the D conjecture. I'll talk about reconstruction theorems and conjectures. I'll mention a little bit some extension of the upper bound theorem, and I'll close by questions regarding enumeration. So part of the pleasure being here is to witness again the striking beauty of enumerative combinatorics and the beautiful formulas. And this field is also very nice, and I hope I can share the enthusiasm with you. So I planned the lecture initially, and I want to start by reminding you what the G conjecture, G theorem is. So we start, so this is part 1. Let K be, I should perhaps one more general remark is that I looked at the participant earlier, and I noticed that there are at least 20, roughly almost 20 people that I know for more than 30 years, and roughly 30 people that I know for more than 20 years. So altogether, it comes up to 1,200 years. Okay, let K be a simplicial D-1 dimensional sphere. And we denote, as usual, Fi of K is the number of I faces of K. And it turns out, this was realized by Peter McMullen, that while these are the obvious, simple parameters for polytopes and for spheres, there are certain linear combinations which plays a special role. And I will just tell you the first few terms. You'll be able easily to see the general formula. So G0 of K is 1, and G1 of K is F0 of K minus D minus 1. G2 of K is F1 of K, the number of edges, minus D f0 of k plus d plus 1 choose 2. And now g3 of k is equal to f2 of k minus d minus 1 f1 of k plus d choose 2 f0 of k minus d plus 1 choose 3, and so on. So given these terms, you can guess the remaining terms, and we go all the way. So we define gi of k for I equal 0, 1 up to d over 2. So Peter McMullen realized that these numbers have a special importance, and the G conjecture, now let me. The G conjecture says that G0, G1 up to GD over 2 arises from a simplicial D polytope. So a simplicial D polytope defines the boundary of a simplicial polytope, define a simplicial D-dimensional sphere. So the G conjecture in its first formulation says that these numbers arises from a simplicial D polytope if and only if there is an order ideal of monomials with G1 variables such that GK is the number of degree K. So let's me call there is an order ideal of monomial S with G1 variable, namely n minus d minus 1 variable, such that dk is the number of degree K monomials in K. So this is the G conjecture as formulated by Peter McMullen around 1970. So 1970, McMullen. And the fact that an order ideal of monomials is a collection of monomial which is closed under taking under divisions. If you have a large monomial and you have some small monomials that divide it, if you have a large monomial in S and a small monomial divided, it's also in S. This condition that these numbers are count the degrees of monomials in an order ideal of monomials can be translated to purely combinatorial relations. This was done already by Macaulay in 1927. And this relation, there is one linear relation which simply says that the GK are non-negative, and there is some non-linear relation of slightly more complicated nature, which tells you the relation between GK and GK plus 1. So this was a McMullen conjecture, and McMullen also said something like maybe this also holds for spheres, namely for triangulations of spheres. We know that the boundary of a simplicial polytope give you a triangulation of a sphere, but not every triangulation of a sphere comes from a boundary of a polytope. And but McMullen was not, he hesitantly also suggested that. There were several development. Maybe I'll tell them quickly. In 1970, as part of a series of work, so actually McMullen and Walkup conjectured the non-negativity of the GIs and also conjectured the cases of equality. And McMullen settled a famous conjecture at the time, which was called the upper bound theorem. I may mention it later, but the upper bound theorem, and this is where these numbers arouse. And McMullen himself also was interested in the question if the upper bound theorem that he proved for polytopes apply to simplicial spheres. Now, what happened next is that in 1975, 5 years after McMullen proof, Richard Stanley used the commutative algebra to prove the upper bound theorem for simplicial spheres. And then in 1980, the G conjecture in its original form was settled. So Bilera and Lee found for every sequence that come from an order ideal of monomial, they found a simplicial polytope that realized this sequence. And Richard Stanley used connection with the hard-Lifshitz theorem to deduce the assertion of the G conjecture. So this was a very remarkable development. And the remaining open question, which remained very interesting to many people in the field, was whether the inequalities that we now know, we knew that they are correct for polytopes, do they apply to all simplicial spheres? And okay, 1 minute. Okay, and this is called the G conjecture for simplicial spheres. And in recent years, there were remarkable achievements. So starting with a paper by Adi Prazito in 2018, and then a paper by R. Rios and Padakis, I think in 2020, and a paper by Adi Prazito and R. Girios and Papa Dakis shortly afterwards. So these 3 papers presented a proof of the G conjecture for triangulated spheres. I will not get to the precise generality that it applied, but I would say that the second paper applied in slightly less generality, but represented a major simplification. And the third paper represented even further simplification, but at the same time extends the result to a large number of objects, including triangulated manifolds. And let me mention another recent paper. So let's call this triple APP. So APP plus Johanna Stenmeyer. So they have a new paper, and this new paper actually deals with not with phase number, but with Erhard polynomial. So with other invariants of convex polytopes, which count lattice points, also extensively studied by Richard Stanley, but their ultimate theorem also extends the G theorem for triangulated spheres. So by now we have a fairly good, I would say, fairly good understanding of the situation. I think what a very important target is to have a proof that can be presented in a graduate course. I think this is the ultimate, the golden rule for any mathematical proof, that you'll be able to present it to graduate students in a course with all the Gary details. And I think we are close to this target. So I should say that once such a major result is achieved, of course, a lot of open problems and further direction will come from the proof itself. But I would like to mention other problems, earlier problems that people thought about, and I before, and some of them are related to various approaches toward the G conjecture. Some of these approaches, of course, didn't lead to the solution. Okay, so this is part one, the D theorem. And now I want to tell you a little bit about the second thing, which is finer invariant. And here the second part will be divided to two small parts. So finer invariants. So we said that the G conjecture asserts that the phase numbers of simplicial spheres and polytopes, they correspond to the degree, the counting, the generating function that count monomials according to the degree of some order ideal of monomials. And indeed, the proof of the G conjecture, both for polytope give you, so I should say, once following the result by Stanley from 75, we gain some understanding what is necessary to be proved about phase ring or Stanley-Reisner ring in order to prove the G conjecture. This is a property which is called the Lefschetz property. And once this property was verified, there are several things that were followed. And so the proof of the G conjecture, it actually gives you an order idea of monomial. So it's provide an order ideal of monomials S of k for every simplicial sphere. Okay, and this order ideal of monomial has one further property, and it is that it is shifted. Let me. So it's a shifted order idea of monomial. Now, shifted means that if x1, x5, x7 belong to S, then also x1, x3, x5 belong to S. So if you take monomial and you reduce the indices of the variables which are presented in the monomial, then this preserves the property of being in this order ideal of monomial. So we can think, so let me say 2a, one finer invariant for simplicial spheres is this shifted order ideal of monomials. So now that we understand completely the phase numbers of simplicial spheres and polytopes, and this phase number don't distinguish between spheres and polytopes, we can think about understanding the finer parameter, which is the shifted order ideal of monomials. So this is a S of k, and I should say there are several remarks I want to make. First, is that for every shifted order ideal of monomials, for every such S, there is a simplicial sphere K of S. So you can start with a shifted order ideal of monomial and get a simplicial sphere. Those simplicial spheres are called squeezed spheres, and which I defined in the late 80s. And Satoshi Morai showed that when you start with shifted order ideal of monomials, go to this simplicial sphere and apply the proof of the G conjecture. Of course, the proof didn't exist yet, but apply the consequence of the Lefschetz property, then you go back to the same S. And another comment is that the number of shifted order ideal of monomials is much larger than the number of simplicial polytopes. We know, due to a result by Goodman and Pollack, that there are not so many polytopes, and this construction allow you to build much more spheres than polytopes. This was even further improved by a subsequent work. So this is the comments, and let me make one more comment. There is an important class of polytopes which are called neighborly polytopes. Those are polytopes which satisfy the upper bound theorem. And the neighborly polytope, when you apply this S of K, you get all the monomials in n minus d variables, and therefore even this fine invariant don't distinguish between neighborly polytopes and neighborly spheres, and it is an interesting question how to distinguish between a neighborly polytope and sphere. So this is the first part of number 2, and let me move to the second part of number 2. So mention some other nice parameters. Maybe I'll do it quickly. We can count not only so let me do it quickly because I want to do other thing, but I should say that we can also count missing faces. So missing faces are collection of vertices, so that every proper subset of the collection is a face, but the entire collection is not a face. So this is called the missing face. And in addition to the list of the face number, you can also add a list of the missing face and missing face numbers. And it turns out that these missing face play a role in the commutative algebra related to simplicial spheres. And in fact, there is an even greater, larger two-index parameters which sum up the Betti numbers of induced subcomplexes. So the I's Betti numbers of induced subcomplexes or of, say, A vertices. So those are some beta ij numbers. And those also provide a very nice finer invariant for simplicial spheres. They were studied by Meglior and all. And in particular, early on, Peter Kleinschmidt, Carly, and I, we conjecture that the missing face numbers and even these more general Betti numbers, if you fix the face number, they are maximized precisely by the Bilera-Lee construction. And it turns out that this was correct. So this gives you some further very interesting invariants. Okay, so let me move to the second topic. I should say so I already mentioned the many people in the audience, at least an hour ago, that I know for many years. So I think the person in the audience I know for most here is Doron Seilberger. So I saw him. So I first met Doron, I think in the mid-70s. And
Again,
what?
let me interrupt with a personal question. This is a beautiful talk so far about combining combinatorics and geometry. Do you think of yourself primarily as a combinatorialist or as a geometer?
So I can tell you one story about Doron, which was even, I think, from one of my first visits to Weizmann Institute when I was, it was just, so this was the late 70s, and I just bought, together with my mother, a car. She didn't have a driving license at that time, but soon afterwards, she completed her driving license. And we had a joint trip to the area of Rehovot, and she had a plan to visit some relatives, and I had a plan to visit Doron. And you know, we entered Doron office, and after about 2 minutes, she got a little bit impatient and said, "Let's move on to our other visits." And then Doron said, "Madam Kalai, I should tell you, your son is a mathematician. He came here to talk to me. So please walk around the Weizmann Institute for half an hour and then come back." And so I remember that I was very flattered. And also my mother was very flattered. And this is what happened. So we talked for some more time on some combinatorial problem and then move on to the further trip we had. Okay, so let me move on to the second topic. And this is a flag number of general polytope and toric G numbers. So we have some more. So let me tell you in general, there are very nice conjectures, which are, so I hope you can see me, but if not, there are very nice conjecture which extend the G conjecture or an analogous to the G conjecture for other classes of simplicial polytopes and spheres. Perhaps the most famous direction is what's called flag sphere. So you start with a graph, you take the simplicial complexes of all complete subgraphs. This is called a clique complex sometimes. And if this clique complex is a sphere, then you're in business. And then there are very beautiful conjectures about this face number of such spheres, and they are related to questions in differential geometry. And I think there is a good reason to believe that the increased understanding of the connection between commutative algebra and algebraic geometry that come to play in recent progress will also contribute to this problem. Okay, so let me tell you a little bit about flag numbers of general polytopes and toric G numbers and about the 3 to the D conjecture. So flag numbers of general polytopes. So you start with a polytope. And of course, here you can also talk about polyhedral spheres and more general objects, but there are a lot of mystery already for the polytope. So let's say that you have a P is a D-dimensional polytope. So what is a flag number? A flag number correspond to several indices, say F2, 3, 5 of P. This is the number of chains of two faces of a two-face inside a three-face inside five-face. So this is the flag numbers. Of course, the face numbers are special case of the flag numbers, but so I hope you can see in your, yeah, okay. So but we have here a much large number of parameters. If you have a simplicial polytope, then the face numbers determine the flag numbers. Actually, even if you have quasi-simplicial polytope, namely all the facets are simplicial, then already the face number determine all the flag numbers. But for general polytopes, you have much more information. And altogether, you see, we have something like 2 to the d flag numbers. And there is a very beautiful theorem by Bayer and Bilera, which asserts that the dimension of the affine space of flag numbers of D polytopes is so. Don, can you mute for a minute your microphone? Because then maybe, because here I see just your screen. And anyway, so Bayer and Bilera's theorem says that the affine space of flag numbers of D polytopes has dimension which is the D Fibonacci number -1. So this is a very beautiful theorem. And another way to say it, that if you look at the Euler relation and look all the relations which are derived from the Euler relation, then this gives you linear dependence of all these 2 to the d numbers. They all can be expressed in terms of Fibonacci number of such terms. And this relates to a lot of nice mathematics. First of all, I should say that flag numbers appeared for general posets already in Richard Stanley PhD thesis, and some of the things that were developed in this thesis come to play in this later work. So this is a beautiful theorem. So we know what is the affine span of all this number, and a major question is what are all the linear inequalities among flag numbers of the polytopes. And this is a very interesting question. I don't think we are close to understanding of this question. And I want to mention some special parameters which give you some non-negative expressions in flag numbers, and they are the toric G numbers. Okay, so let me just before I talk about toric G number, I mentioned the Bayer and Bilera theorem. So part of the theorem was to prove that the Euler relation implies that only that the dimension is not larger than a Fibonacci number -1. But there was another part, which is to construct sufficiently many polytopes, Fibonacci number of polytopes, where the flag numbers are affinely independent. And I can tell you how Bayer and Bilera did this. They consider polytopes which are expressed by word of the form B, P, B, P, 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 B, P, B, P, P, for example. And every such word, so these are words in P and B without 2 consecutive B's, and every such word, and it also needs to start with P, and every such word applies to one of 2 operations. P applies to the operation take a pyramid, and B applies to the operation take a bipyramid. And when you do all this operation together, you get a large number of polytopes, and Baer and Bilera managed to prove that their flag numbers are linearly independent. And then there are other works with other classes of polytopes that I will not mention, but and they also relate to nice, I would say, enumerative combinatorics. But I want to explain what are the toric numbers. So one way to describe the toric G numbers, so maybe I will just give you where they come from. So as I said, Stanley proved the GCOM for spheres using the hard-Lefschetz theorem for toric varieties. And the reason it works is that when you look at toric varieties, it's certain algebraic varieties which correspond to simplicial spheres, those varieties are close to being smooth. When you start from general polytopes, you get a very complicated varieties with very unpleasant singularities. But nevertheless, these objects have some nice homology numbers based on the so-called intersection homology. So the toric G numbers comes from intersection homology of toric varieties. Okay, maybe I'll not go into detail. I'll just say that the G numbers are they are linear combination of flag numbers. And with 5 more minutes, I could show you the how it works. But this fact, the fact that the G numbers are dimension of intersection homology implies immediately that the GIs are non-negative. But so now I can tell you what I regard as the most central, or perhaps even the central problem in this area of algebraic combinatorics is that we don't know that the GI are degree numbers for order ideal of monomials. And so there is a conjecture that G0, G1 up to GD over 2 is an M sequence. Namely, there is order ideal of monomials, that those are the ideals of, those are the monomials of degree K. And this is a very frustrating conjecture, because when you look at the explicit examples, it looks that situation is even better. The inequalities hold even stronger for the general polytopes. On the other hand, intersection homology lacked the ring structure which was needed to prove this property in the simplicial case. So again, if you didn't see it before, this was too hand-wavy and not too concrete, but I think this is a lovely conjecture. And I should say that we now don't think that the toric, unlike the simplicial case, the toric G numbers seems to provide only small information on even on linear inequalities for flag numbers. We don't know what other combinatorial or algebraic gadget will help us to further push this theory. There is also a very interesting suggestion supported by some results of Eran Nevo, that maybe some question about phase numbers of polytopes, general polytopes, or other classes of polyhedral complexes or simplicial complexes are computationally difficult. So this world of full characterization that we had in the early part of the theory, maybe there are some in-principle reason why it cannot continue. Okay, so I want to move to another topic, which is the 1 minute, which is the 3 to the D conjecture, and here, and this is a very, very simple, unlike the toric G numbers, that it will take some effort to explain what they are, and even more effort to motivate or to explain where they come from. Here is a very simple, some very simple questions, and this is the following. So now let's talk about centrally symmetric polytopes. So let P be a centrally symmetric D polytope. So centrally symmetric means that if X belongs to P, this implies that minus X belongs to P. And then there is the following conjecture. F0 of P plus F1 of P, so on, plus Fd of P. So here Fd of P is 1. This is just for the entire polytope, is greater or equal than 3 to the D. So this is a conjecture. Let me mention another conjecture, which is sometimes called the flag conjecture for a D polytope, which says that F0, 1, 2, and so on up to D minus 1. So the number of maximal chains or faces is greater or equal to 2 to the D times D factorial. So those are two very simple conjectures regarding centrally symmetric polytopes. The case of simplicial polytopes, it follows from results by Barani and Lovash and by Richard Stanley. And we know we have, I would say, pretty good understanding of phase numbers of simplicial polytope. But here, the point of this conjecture that the polytopes are not simplicial. Where are these numbers coming from? So these numbers are coming from the cube. So if you look at the cube, the number of vertices, let's say the cube in 3 dimensions, it have 8 vertices, 12 edges, 6 faces, and the cube itself, this is 27. And it also satisfies the second conjecture. And the point, I think one reason that this conjecture might not be as easy as it seems is that there are many cases of equality. So of course, if the cube is a case of equality, then also its dual, the cross polytope, is a case of equality. But you can start with 2 polytopes which satisfy this conjecture with equality, take their Cartesian product, and you will get still another such example. And also you can again take the dual. So this gives you a fairly large class of polytopes that satisfy this conjecture as with equality. And this class of polytopes are called Hanner polytopes. And this is I think it's a very nice conjecture. We don't know how to relate this conjecture to any of the machinery, either from commutative algebra or from algebraic geometry, but we may be able, this may come at a later stage. But it's interesting that these conjectures are related to conjectures about centrally symmetric polytopes and centrally symmetric bodies. So I already mentioned in the beginning that recent work by some recent work show some connection, or we already knew some connection when we move from the study of phase number to the study of lattice points in polytope. Now there is, if you talk about the combinatorial theory, which is the study of phase numbers and the phase structure, the arithmetic theory, which is the study of integral points in a polytope. There is also the metric study, which study metric parameters like volume and such object. And indeed, there is a connection of this conjecture with a rather well-known conjecture, which is called the Mahler conjecture. So Mahler conjecture, and Mahler conjecture asserts that if K is a centrally symmetric d-dimensional body, then the volume of K times the volume of the dual of K is greater or equal than 4 to the d divided by d factorial. The 4 to the d divided by d factorial is what you get when you take K to be the cube. And again, equality holds for all Hanner polytopes, and conjecturally only for them. And it turns out, so there are some recent work which relates this combinatorial conjecture and this metric conjecture, but let me mention some earlier connection that and this is that this is the following relation. So this is another conjecture. If you look at the number, if you have a centrally symmetric polytope in d dimension, you look at the total flag numbers, then this is greater or equal to the volume of P times the volume of the dual of P times d factorial square divided by 2 to the d. So this conjecture also gives you a connection between this metric conjecture, Mahler conjecture, and those combinatorial conjecture. But I should say that recent work by several researchers explore some deeper connection, and in particular, they have a certain differential geometry conjecture that in one extreme give you the combinatorial conjecture, in the other extreme give you a Mahler conjecture. Okay, okay, let me conclude. Okay, so I should say, let me conclude with two problems that I will mention very briefly because I'm running out of time. Yeah, I have 2 more minutes, so I will just mention 2 conjectures. So maybe I'll just mention it without a blackboard. You see? Okay, so the first question is about reconstruction. Actually, there are a lot of. Do you see me or? Yeah,
this is better. I think if you stay here.
Okay, so the first question is about reconstruction. There is a theorem by Blind and Money. Later, I found a nice, simpler proof than their proof that the graph of simple polytopes determines the entire combinatorial structure. In other ways, if you know the relation between facets and between faces of top dimension and one less than the top, if you know the incidence graph between facets and subfacets in a simplicial polytope, this gives you the entire combinatorial structure of the polytope. And this proof relies on shellability, but on stronger form of shellability. So, and a very basic question is to find, to extend this result to all simplicial spheres. So to show that every simplicial sphere is determined by the incidence relation, by the graph of incidences between facets and codimension one facet, or another way to call it is every simplicial sphere is determined by its puzzle. The puzzle is an abstract graph where you think about the facets as pieces of puzzle, and two facets are adjacent if they share a codimension one face and the codimension two face. And this is not known, and it's not even known for shellable spheres. And it looks that the machinery of Stanley Reisner ring and commutative algebra may contribute something to this question, but this is not known. And the last question I want to mention is the question of enumeration, although not about precise formulas, about asymptotics. How many, for example, how many simplicial three-dimensional spheres are there with n facets? So we count them up to isomorphism type. If we're talking about simplicial two-dimensional faces, there is a rich theory by Tat, and with a lot of beautiful extension, and in particular, the number is exponential, and we know even fairly good about the exponents themselves, but it's not known in dimensions for three-dimensional sphere. It's not known that this number is exponential in the number of facets. It is known for shellable spheres, but it's not known for general spheres.